Well, it's my pleasure to introduce our speaker for today. So Mohan Swaminathan from Princeton, and he's going to tell us about super-rigidity and embedded curves in Calabi-Yau threefolds.
So thanks a lot to the organizers for the opportunity to speak in this seminar. So before I get started, I just want to mention that this talk is based on joint work in progress with Shaoyun Bai, who is also a grad student at Princeton. So, okay, so here's the rough plan of the talk. So parts 1 and 2 will be sort of the main portion of the talk, and I will focus slightly less on 3 and 4. So part 1, I will give some relevant background on embedded curves in Calabi-Yau threefolds and the super-rigidity result of Wendl. In part 2, I will use this to describe bifurcation analysis for moduli spaces of embedded curves in a certain model case. Then part 3 will develop an application which is to constructing an integer valued count of embedded curves in the model case that I talked about in the previous section. And part 4 is about the further directions that we can go from what I talked about. Okay, so let's get started. So the first piece of background is the virtual dimension formula for Calabi-Yau threefold. So if X omega is a closed symplectic Calabi-Yau threefold, then for any choice of compatible almost complex structure and any genus and any homology class beta, the moduli space of genus G stable J holomorphic maps of class beta has virtual dimension 0. So this follows from the computation shown here, which is the virtual dimension is twice n minus 3 times 1 minus G plus the Chern class paired with beta. And both terms here vanish because n is 3 and C1 is 0. So what this tells us is that Gromov-Witten invariants for Calabi-Yau threefolds are a collection of rational numbers. So one for each genus and homology class. So I denote these by capital N G beta. So these are only rational numbers because the curves we are counting might have automorphisms. So they have to be counted with 1 over the cardinality of the automorphism group. So that gives us denominators. So a natural question might be, are there underlying invariants which count curves with values in integers from which we can reconstruct the Gromov-Witten invariants? So this is a very well-known question with a well-known answer. So physicists Kobokumavalfa defined something called BPS invariants. So I'm denoting these by small n G beta. And while the definition is physical, and I mean, there are many proposed mathematical definitions, sort of the major important prediction Kobokumavalfa make is this identity right here, which relates the Gromov-Witten generating function to the Kobokumavalfa invariants. So one thing you can immediately see from this formula is that either side determines the other. That is, if I knew the capital N's, then I can reconstruct the small n's, and vice versa. If I knew the small n's, I could reconstruct the capital N's. So you could view this as a definition of the small n's, and then you can ask, are the small n's defined this way integers? And indeed, this happens to be the case, and this was proved by Wendl and Parker in 2018. So what's strange somehow about this proof is that we don't know what little n's are. We just know that they satisfy this formula, and we know that they're integers. So intuitively, little n's should come about by separating the simple and multiply covered contributions to the Gromov-Witten invariant. So intuitively, the simple part would contribute integers, and the multiply covered part would somehow depend on the simple Gromov-Witten, sort of the simple counts for smaller genus or smaller homology class multiplied by suitable rational numbers. So then we may ask, can we directly define integer valued invariants by counting embedded curves? So let's try to think about this a little bit. So we can achieve transversality for generic J for embedded curves. This is the usual argument, but compactness is going to fail in general. That is, a sequence of simple or embedded curves is not necessarily going to converge to a simple or embedded curve. So suppose that Jn is a sequence of almost complex structures and fix the genus and homology class. Then a sequence of embedded Jn holomorphic curves sigma n might converge to a multiple cover of an embedded J holomorphic curve. So the embedded curve is shown in pink, so that's sigma, and it has a possibly branched multiple cover, which is sigma prime, and this is the Gromov limit of the sequence sigma n. So, so below you see a schematic picture of this, and here we have depicted sigma as the zero section within the normal bundle. So the normal bundle is embedded within X as a tubular neighborhood. And sigma n for n large lies within this tubular neighborhood. And it looks like a section of the normal bundle of sigma. So more precisely, because sigma n is mapping as a multiple cover onto sigma, this is really a multi-valued section of the normal bundle. So now you could imagine the C0 norm of this multi-valued section is going to 0 because sigma n's are converging to a multiple cover of sigma. So what you could do is rescale each of these multi-valued sections so that their C0 norm is exactly 1, and then try to take a limit of this. So what this leads to is the following. The normal deformation operator of the curve sigma. So this acquires a non-trivial kernel when pulled back to some branched cover. So this branched cover is nothing but the limit of these sigma n. So think of each sigma n mapping down to sigma via the projection of the tubular neighborhood. So this is an approximately holomorphic branched cover. So as n goes to infinity, this is a genuinely holomorphic branched cover. And we have a section of this normal Cauchy-Riemann operator defined on this branched cover. So in other words, what this is telling us is that a sequence of embedded curves might converge to a multiple cover of another embedded curve precisely when this happens. Namely, the normal deformation operator acquires the kernel, possibly after pulling back to some branched cover of another embedded curve. Okay, so based on this, we make the following definition. So this is an almost complex structure J, which is compatible with omega. So Jx omega is my notation for that, is said to be super rigid if the following 3 conditions hold. So condition A is any simple J curve is embedded. So I should have mentioned this before, but I am sort of using embedded and simple interchangeably, basically because for a generic J on a Calabi-Yau threefold, we can ensure that these two are the same. Condition B is that any 2 embedded J curves are disjoint or identical. And part C, which is sort of the most important condition here, is that for any embedded J holomorphic curve sigma in X and any degree D bigger than or equal to 1, the normal Cauchy-Riemann operator D and sigma J is injective even when pulled back along any D to 1 branched cover sigma prime to sigma. So this is a holomorphic branched cover of Riemann surfaces. So I just want to make a small remark that A and B are satisfied for J outside of a set of codimension 2 inside Jx omega. So we are not going to focus on those 2 conditions anymore. We will instead focus on C, which is the most non-trivial condition defining super rigidity. So, right. So now let's ask ourselves, what happens when C fails? So when C fails, we know that there's a branched cover of sigma and embedded curve, so that the normal operator acquires the kernel when we pull back to this branched cover. So first, as a reduction, we can assume that the branched cover is actually Galois. So in other words, a regular cover after removing the branch points. So this, and let's say the Galois group of this cover is G. So then this cover also sits in a certain finite dimensional moduli space of branched Galois covers of sigma. So this moduli space is described by 2 pieces of data. One is the group G, and the other is its combinatorial type. So this I'm denoting by B. So this is just given by the number of branch points, the ramification indices, and the associated permutation representation, which sort of, I mean, the image of this permutation representation is given to be isomorphic to G. So that's a branch, a moduli space of branch covers in which U sits. And the last piece of information is the kernel and co-kernel are both non-zero. So remember that I required the kernel to be non-zero, but we can show that the index is always less than or equal to 0 here. So the co-kernel automatically must also be non-zero. And these, which I'm abbreviating by the orange K and C, are both finite dimensional vector spaces, which are naturally representations of G. So the fact that representations of G is clear from the fact that sigma prime is a Galois cover over the pink curve sigma with Galois group G. Okay, so I call any such piece of data a witness to the failure of super-rigidity. So we can collect all these witnesses in certain universal moduli spaces whose dimension we will next discuss. So here are the relevant moduli spaces. So here, gray star, so I wanted to focus on the second thing for the moment. So the second moduli space here is, so within parentheses, we have the moduli space of embedded genus G curves in class beta in the manifold X, and with respect to any compatible almost complex structure. So in other words, think of this like a universal moduli space that you use to prove transversality. But in addition to such an embedded curve, we also give ourselves the data of a branched cover of this embedded curve, which belongs to the combinatorial type B and is given with a fixed isomorphism of its Galois group with G. So that's what is our bigger space. The smaller space that includes into it is described by the locus where the kernel and the co-kernel of the pullback of the normal operator to the branched cover is isomorphic to two given representations, K and C. So in other words, the data that goes into defining the smaller object in this inclusion is firstly the genus G, the homology class beta, the combinatorial type B, the Galois group G, and two finite dimensional representations K and C of this group G. Okay, so so now we can ask ourselves, what is the dimension of this smaller space? So in other words, what is the codimension of this inclusion? Because the bigger space is, of course, fairly easy to understand. So, so now we have sort of the main theorem on which a lot of this talk rests on, which is this theorem of Wendl's from 2019. So in his archive preprint, which I've listed here, it's listed as theorem D, or the stratification theorem. So the theorem states that the inclusion star has codimension given by the dimension of the following vector space. The vector space is the space of G equivariant homomorphisms from the kernel representation to the co-kernel representation. Okay, so, and also, I mean, this is not true just as stated without the caveat in brackets. So the caveat in brackets is that this holds away from a subset of the almost complex structures of infinite codimension. So this caveat is not that big a deal when you're dealing with any finite dimensional generic family of almost complex structures, because you can always perturb them to lie away from this bad infinite codimension subset. Okay, so so a corollary that follows from this, which is not entirely obvious, but I mean, it uses the fact that we are in a Calabi-Yau threefold or higher dimension. Is that the complement in the space of all almost complex structures of the locus of super rigid almost complex structures has codimension at least 1. So in other words, the non-super rigid J's form a subset of codimension 1. So in particular, a generic J, so generic in the bare sense, is super rigid. So so now maybe I just want to say a couple of words about how Wendl's theorem is proved. Rather, I want to give a very, very high-level sketch of how it's proved. The actual proof has a lot of non-trivial details, which I will not get into here. So so yeah, so let me first start by going back to this inclusion. So in this inclusion, for any point in the big, yep.
But this corollary, so if the K and C are very different simple representations, it seems that there is no homomorphisms. So why the codimension is 1 in that case?
I'm sorry?
You have K and C are representation of G, right? And if they are different simple representations, representations, there is no homomorphism.
Yeah. So, but I mean, okay. So in fact, I mean, maybe I should have said that for K and C, I mean, not every K and C will have a non-empty stratum. So some strata will just be empty. So I mean, the non-empty ones will have this codimension, which is hom G, K, comma C. So in fact, we can, I mean, the choice of K and C is not completely arbitrary. We can actually figure out what possible Ks and Cs would occur. So
so you say that the two different irreducible representation cannot appear as such a kind of thing.
Yeah.
Okay, thank you very much.
Okay. Yeah. So let us go back to this. So I just wanted to explain sort of how this vector space hom G, K, comma C is actually going to show up in our picture. So here we have, so each point in the bigger moduli space here has a differential operator associated to it, namely the pullback of the normal operator of the embedded curve to the Galois cover. So now this thing is a G equivariant operator. So I mean, there is a G action on both the source and the target. And so we want to sort of write down an equation, a local equation for this smaller moduli space within the bigger moduli space. So my claim is that there is an equation for this smaller moduli space inside the bigger moduli space, which takes values in this finite dimensional vector space hom G, K, comma C. And then Wendl's theorem sort of reduces to proving that this equation is cut out transversely. So that is really the non-trivial portion of the proof, which I'm not going to talk about. I will just quickly describe how we actually get this equation. So before this, I just want to think about a simpler case. So think about E and F, which are just two Banach spaces, and consider the space of all Fredholm operators from E to F. So this is an open subset of the space of all bounded operators from E to F. And for any two integers K and C, we can look for the subset which corresponds to those operators for whom the kernel is K dimensional and the co-kernel C dimensional. And this is something you might know, you might be familiar, is actually a codimension KC locally closed submanifold of the Fredholm operators. And how do we prove this? So, so let me just quickly talk through this in words. So what we do is we take an operator D from E to F, which has kernel K dimensional and co-kernel C dimensional. And then we split off the kernel from E and the co-kernel from C. So we pick a summand for the kernel and a summand for the co-kernel. And with respect to this, we can write down the operator D as a block matrix. And now, anytime, I mean, in which three blocks will be 0 and only the block corresponding to the two complements of the kernel and the co-kernel, that block will be an isomorphism. And now if you perturb this matrix slightly, then it's easy to see that we can do some row operations and column operations to make this matrix triangular. And its kernel and co-kernel will be entirely governed by this finite block in it, namely the block corresponding to hom from kernel of D to co-kernel of D. And so basically, so the way this equation, this local equation around D comes about is you write every nearby operator in this block decomposition, and then you write down what happens in this small block when I do the appropriate row and column operation. And when this small matrix vanishes is precisely when you stay on this subvariety. So in this case, it's very easy to prove transversality, namely that this equation is cut out transversely. But in Wendl's case, so we proceed in the same way, namely we choose a G equivariant complement for the kernel and the co-kernel, and we write down the equation in the same way. But it's substantially more non-trivial to actually prove that the equation is cut out transversely this time. I mean, famously because, I mean, with equivariance, it's quite hard to achieve transversality. So this requires some sort of new ingredients in the proof, which are different from the standard transversality proofs. And yeah, this is something that I'm probably not going to spend too much time talking about. So maybe this is a good time to ask, are there any questions about this introductory part? Okay, so I guess not. So then maybe, so that concludes part 1 of the talk. So let's get to the next part. So, so now we have the super-rigidity theorem of Wendl under our belt. So now we can start trying to analyze embedded curve moduli spaces. So let's start with the following observation. For any super-rigid J, there is a well-defined count of embedded curves for any given G and beta. So what is the reason for this? Well, any embedded curve firstly is cut out transversely by the assumption of super-rigidity, right? Because its normal Cauchy-Riemann operator is supposed to be injective, which because of index reasons means it's also surjective. And so each embedded curve is actually cut out transversely. So it's an isolated point in its moduli space, and it has a well-defined sign associated to it. And secondly, there are only finitely many of these, because a sequence of embedded curves cannot converge, as we have seen, to a multiple cover of a different embedded curve, precisely because of this super-rigidity assumption. So therefore, we have a count of embedded curves for any genus and any homology class beta. But of course, the catch is that this depends on the choice of the super-rigid J. So what we see is that a generic path of almost complex structures will in general fail to be super rigid at a discrete set of times. So this is precisely because the space of non-super rigid J's are codimension 1 in the space of all J's. So we will have some wall crossing or bifurcations occurring. So this is exactly the subject of this section. So we need to understand how the count of embedded curves changes when we cross one of these walls. And if we want to define an invariant count of embedded curves, then we would want to attach a suitable correction term to this, which compensates exactly for the wall crossing term. So there's a precedent for this that we find very useful, which is Dobbs's 1996 construction of the Gromov invariant for symplectic 4 manifolds. So this is the invariant he constructs. So this is one side of the famous SW equals GR theorem. But the Gromov invariant is defined by counting embedded curves, but it turns out again that there is a problem of bifurcations there for a specific kind of tori. So embedded tori of self-intersection 0, it turns out can experience bifurcations in one-parameter families in Dobbs's construction. So he does a careful analysis there to figure out sort of what correction terms to exactly add so that we get an invariant count independent of which super-rigid J one chooses. So, so in our case, we use a very similar idea. I mean, there is a little more work to do because there are branched covers as opposed to unbranched covers of tori. So not only do we have to consider normal bundle perturbations, we also need to consider the perturbations of the branch points to get the whole moduli of holomorphic curves. And the wall structure to us in this case is given by Wendl's theorem. And so sort of combining these two ideas, we are able to study these bifurcations. So I will be illustrating this in detail in the following important case. So this is sort of the first important case after the primitive case where everything is obvious. So let's take the genus to be 0 and the homology class beta to be twice a class A. So A is a second homology class, which is primitive for the symplectic form omega, which means that it's firstly a class with positive symplectic area, but cannot be broken into two classes with strictly positive symplectic area. So, so counting embedded curves in class 2A is something that is not entirely obvious because a sequence of embedded curves of class 2A might limit to a double cover of a curve of class A. Okay, so now, yeah, so we ask ourselves what kind of bifurcations are possible in this case. So, well, I mean, a sequence of curves of class A or a sequence of curves of class 2A might converge to a sequence of rigid curves can converge to a non-rigid such curve. And this is actually dealt with in the usual sort of familiar way, which is birth-death bifurcation. So these will just look like, so these will just look like this. So if this is a one parameter family of J's, then if the moduli space is 2 points here, then it might be that these two curves come together and die beyond this point where the bifurcation takes place, or it could be that they're born beyond a certain point where the bifurcation takes place. So in this case, it turns out that these two have opposite signs, so this does not affect the count. So these are standard bifurcations, but a new bifurcation that we need to consider here is a sequence of rigid two-way curves converges to a double cover of a non-super rigid A curve. So let me say that again. So you have a sequence of two-way curves for a sequence of almost complex structures, and these converge to a double cover of an embedded A curve. So this A curve, therefore, by definition, must be non-super rigid because it has a 2-to-1 cover, to which if we pull back the normal Cauchy-Riemann operator, we have a kernel. Okay, so this is the case that we are going to describe in detail. So basically, we are going to construct a local Kuranishii model for this, and I'm going to describe how one analyzes this local Kuranishii model and what we can draw as a conclusion from this to define an invariant count of embedded curves of class 2A. Okay, so right. So now, so first, before we begin, we need to understand what is the wall that governs this bifurcation. So let's take a look at this this picture here. So let me explain the various terms here. So firstly, J is what I was earlier denoting as Jx omega, which is the space of compatible almost complex structures. So this is a Fréchet manifold, and over this is sitting the space of embedded J holomorphic curves of class A of genus 0. And this map, this vertical map that you see is an index 0 map, right? This is just the dimension formula. And then over this sits a bundle which consists of not only the data of an embedded A curve, but also along with it a double cover of this embedded A curve. So that is a 2-to-1 genus 0 cover of this. So which just looks like Z goes to Z square if you put standard coordinates on P1. And this always has, I mean, this is always Galois with Galois group Z mod 2. And so there's no need also to specify the branching data here because we know that each branch point has precisely one preimage of multiplicity 2 over it. Okay, so now notice that this upper vertical arrow is actually a subversion with fibers which are isomorphic to the moduli space of double branch covers of P1 of genus 0. So this is a this has complex dimension 2, and so this is a projection whose Fredholm index is 4. The second projection has Fredholm index 0, so this composite has Fredholm index 4. Okay, so that's the first thing. The second thing we need to consider is the space of such data which constitute witnesses to the failure of super-rigidity. That is, we have a curve of class A and the data of a double-branched cover, and we have a kernel and a co-kernel which is non-zero. So let me say here that I'm taking the kernel to be the sign representation of Z mod 2. So this is just the obvious one-dimensional representation on R of Z mod 2, where the non-trivial element acts by -1. And the co-kernel is 5 times the sign representation. So why is this the representation we need to look at? Well, firstly, we are looking at those curves where the kernel of the pullback of the normal operator is non-zero. So moreover, we have a sequence of two-way curves which are coming and converging to this to a double cover of this A curve, which means that we must have a kernel element which is acted upon non-trivially by Z mod 2, which means there is at least one copy of the sign representation in the kernel. Now, that immediately tells you that there must be at least 5 copies of the sign representation in the co-kernel just by an index computation, because the index of this operator is -4. And now we can then check that if we take any, if we take this particular stratum, namely those with kernel, the sign representation, and co-kernel, the 5 times the sign representation, this is a codimension 5 inclusion inside this space of double covers of embedded A curves. And so what this means is that this composite map from this thing encircled in green to the space of almost complex structure is an index -1 map, which means you should think of this like a codimension 1 cycle inside J. So this is why it deserves the name of a wall. And this also immediately tells you that if the kernel was something that was bigger than just the sign representation, then this would not be a wall. That is, it would be of higher codimension. So we can ignore it for 1 parameter families of almost complex structures. So that's what I have written here below, which is that a generic path of almost complex structures will meet the wall transversely at a discrete set of times. And we need to ask now what happens at these times. So we need to understand what is the local structure of the moduli space near such a point. So, before I proceed, maybe are there any questions at this point? Okay.
I have a quick question.
Yep.
Very quick question. So you're assuming that the class is omega primitive. So if the assumption is not there, then essentially you don't expect a sequence of of embedded curves to converge to a branch cover, right? Yeah, it could be that it just converges to a stable map that has an additional component. Is that why you put the assumption?
Not exactly. I mean, so remember that we had in the definition of super-rigidity 2 assumptions, which said that any 2 embedded curves are either identical or disjoint, and that every simple curve is embedded. So this is an assumption that holds for all J outside of a codimension 2 subset. So this means that these are the only J's we actually need to consider in any 1 parameter family of J's. So what this means is that you cannot have a stable map which has sort of components which are essentially geometrically distinct. I mean, whose images are distinct.
Okay.
So you could potentially have a nodal stable map, all of which maps onto a given embedded curve with an X, but you can't have sort of a stable map which looks genuinely like 2 different curves meeting one another. So,
thank you.
Okay.
I have a question. Sorry. So the index -1 map, does this map embedding? Is it
this map?
embedding? Is this index -1 map? Is it embedding?
No, it's well, I mean, it's not obvious at all that it's an embedding, at least. I mean, it's just an index -1 map. So when I say meeting the wall, you should think more precisely as I have a path in J and I take the fiber product, and that will have finitely many points.
And does it map to the non-super-rigid part?
Yeah, it does, right? Because I mean, by almost by definition, because these are sort of curves where there is a non-trivial kernel when you pull back to a double cover.
Yeah. Okay.
Yeah, so I mean, this is just a specific part of the non-super rigid ones, but yeah, I mean, this is the one we are looking at to analyze this particular bifurcation.
Okay, I see. Thank you.
Okay, so maybe I will proceed further. So, right, so let's say gamma is this generic path in the space of almost complex structures, and let's say that it meets the wall. So the wall is the thing in green before. So the encircled moduli space is the wall. And so let's say that this path gamma meets the wall at time t equal to 0 at a 2-to-1 cover. So this 2-to-1 cover has 2 parts. One is this pink curve sigma, which is an embedded curve of class A with an X, and sigma prime, which is a 2-to-1 holomorphic double cover of this curve sigma. So U is the covering map. And our assumptions are exactly saying that the kernel of the pullback of dn sigma along U is the sign representation, and the co-kernel is 5 times the sign representation. So in particular, what this means is that the kernel and co-kernel of dn sigma themselves are 0, because if not, then this yellow kernel and co-kernel would have trivial sub-representations as well, right? Because you would have a kernel pulled back from the lower curve sigma, and so on that Z mod 2 would act trivially. So therefore basically this assumption is telling us that the underlying embedded curve sigma is actually cut out transversely. But not only this, for simplicity, I will also assume that the sign of this embedded curve sigma is +1. So in other words, being a transversely cut out embedded curve, sigma has a sign associated to it, a plus or minus 1. I'm going to just assume that this is +1 for simplicity. Okay, so now I claim that transverse intersection with this wall implies that we have an isomorphism such as this. So let me first quickly describe the terms here, and then I will sort of justify why we get this isomorphism. So T0 gamma is just the tangent space to the path gamma at the point 0. So this is just a copy of R, just the parameterizing space of the path. M0 sigma 2 is the space of branch covers of sigma of degree 2. So these are just 2-to-1 covers of P1 to P1. And this is the tangent space of that at this chosen branch cover U. And on the right side, we just have the Z mod 2 equivariant maps from the kernel to the co-kernel. So of course, Z mod 2 equivariant maps in this case are just maps. I mean, just linear maps, because both sides are just, contain the same representation, namely the sign representation. Okay, so, right. So how does this isomorphism come about? Well, for that, let's again look at this picture. So imagine that you have the path gamma sitting inside here. And so what we're trying to do is understand the fiber product of this wall with this inclusion of gamma inside J, right? That's what counts as an intersection of gamma with the wall. Or in other words, imagine sort of pulling back the wall and just looking at the portion that lies over gamma. So how do we understand this? Well, the portion, so first let's take the inverse image of gamma within this moduli space. So because this moduli space, gamma is a one-dimensional submanifold, and this projection has relative dimension 4. So when you pull back gamma, you would expect that this thing is a 5-dimensional submanifold. So we're trying to figure out whether this 5-dimensional submanifold meets this codimension 5 submanifold transversely at the point that we had chosen. So to check this transversality, we need to look at the tangent space of this 5-dimensional manifold and the normal space of the codimension 5 submanifold. So as I said in my very sketchy introduction to Wendl's theorem, the normal space is precisely given by the Z mod 2 equivariant homomorphisms from kernel to co-kernel. So that's precisely the right side of this isomorphism. So that's the normal space to that codimension 5 submanifold, and the left side is the tangent space to this 5-dimensional manifold. So saying transverse intersection is precisely giving us an isomorphism like this. And I'm calling this isomorphism star. So again, to simplify some sign computations later, I'm going to make one more assumption, which is that I'm going to assume that this isomorphism preserves orientation. So what I mean here is the following. So the left side has an orientation because the path firstly is oriented and M0 sigma 2 is complex. And the right side you can check can be oriented by the usual sort of determinant bundle type trick. So so I will maybe not dwell on that too much. And we will now go to construct the Kuranishi model for the moduli space of gamma t holomorphic stable maps near this particular base point, which is sigma prime comma u. And remember that just constructing the Kuranishi model is not enough. We sort of need to figure out which of these are the embedded curves and which of these are the not embedded curves, so that we can figure out precisely what is the change that takes place in the moduli space of embedded curves. Okay, so let's first recall sort of how one constructs the Kuranishi model. So you have some nonlinear Fredholm setup, and you have the kernel of a linearized operator at a point and the co-kernel. So what you do is you're trying to, and you have an equation, a Fredholm equation, which is cutting out the moduli space that you want. So now, because this linearization is not surjective, it means that we have a co-kernel. And so if we pick a lift of this co-kernel and look at the equation modulo this lift, then we have something whose linearization is surjective. And so we look first at this obstructed equation, and we get a finite dimensional moduli space whose tangent space is precisely the kernel of the original linearized operator. But this finite dimensional moduli space now still carries a function with values in this obstruction space. And so this is the finite dimensional Kuranishi model that we get. So with that in mind, this assertion should be clear, which is that the Kuranishi model will be a Z mod 2 equivariant germ at 0 of a smooth map, which goes from this source to this target. So the source is a copy of R, namely the tangent space of the path, the tangent space of the space of branched covers at U, the normal kernel, and all of this maps to the normal co-kernel. And F is the name I'm giving to this map. So think of this just as a germ of a map defined near 0. Moreover, this map has to be Z mod 2 equivariant because, I mean, our initial point has Z mod 2 symmetry, and we can choose sort of all the complements and other things that were used to apply the implicit function theorem to extract the Kuranishi model. We can choose all of these in a Z mod 2 equivariant fashion. So our Kuranishi model now is given in the following way. So before this, I just want to, because I want to write this model down very explicitly, I want to choose coordinates on my source and target. So my source, so T0 gamma, I choose a coordinate T on it. So this is just the obvious coordinate, namely the parameter of the path. In the space of branched covers, the tangent space is given by how I vary the 2 branch points. So this I can sort of trivialize the tangent spaces at these 2 points by C. And so 2 complex numbers give me the variation of this branched cover. So that's Z1 and Z2. These are the coordinates. And then the kernel is a 1-dimensional vector space. So I just choose some non-zero generator S of the kernel, and I pick a corresponding coordinate epsilon. Basically, any section is epsilon times this generating section S. And finally, I choose a coordinate on the co-kernel. So the co-kernel is 5-dimensional. So I need to pick a coordinate function W that takes values in R to the 5. So sort of the first 3 coordinates that I chose were chosen more or less without any serious thought, but the last one needs to be chosen somewhat carefully. So the last one needs to be chosen so that the following holds. So look at this isomorphism star. So in the isomorphism star, we have so far trivialized the left side completely. So the left side looks like R direct sum C squared, and the right side looks like Hom from the real line into a certain 5-dimensional vector space, which we have not yet put coordinates on. So, and this is an isomorphism. So therefore, what we can do is put the coordinates on the co-kernel so that this isomorphism is precisely given by the identity map. So, so to say that once again, I choose the coordinates on the co-kernel so that the map star is precisely the 5x5 identity matrix. Okay. So now the Kuranishi map is given in the following way. So W is equal to F of T, comma Z1, comma Z2, comma epsilon. So notice that I have sort of color coded these variables. So the blue variables are the ones on which Z mod 2 is acting trivially, while the orange variables are the ones on which Z mod 2 is acting non-trivially. So this means that this function has to be odd in epsilon. So if I substitute minus epsilon for epsilon, then W will change to minus W. Okay, so now my first claim is that this function F is actually divisible by epsilon. So in other words, it can be written as epsilon times G of T Z1, Z2 epsilon. And why is this? So to show this, we just need to argue that if I set epsilon equal to 0, F will vanish. So why is this? Well, if I set epsilon equal to 0 and give myself a small t, a small z1, and a small z2, I can argue as follows. So remember that the embedded pink curve sigma was cut out transversely. So if I take a small t, then there is a unique way to deform this curve using inverse function theorem to a gamma t holomorphic embedded curve that just lies nearby sigma. And now, given my z1 and z2, I can choose the corresponding branched cover of this curve, and this will give me a bona fide holomorphic curve. and not merely an obstructed holomorphic curve. That is a holomorphic curve with which is sort of del bar is 0 up to obstruction. Rather, it will be 0 on the nose. So what this tells me is that whenever epsilon is 0, I can actually solve the holomorphic curve equation exactly, and I don't have this obstruction term remaining as non-zero. So what this tells me is that f vanishes at epsilon equal to 0. And that immediately tells me by dividing by epsilon that I get a smooth function g of t, z1, z2, and epsilon. And now g has the property that it is no more odd in epsilon, but rather is even in epsilon, because we have sort of removed the odd part by taking out the factor epsilon. Okay, so now, so is this, so yeah, if there are questions, please feel free to ask. Okay, so now the next thing we need to do is figure out the next terms in the Taylor expansion of this map F. So let's look back here. So G, remember, was an even, is a function which is even in epsilon. So so it's easy to show that G vanishes at the origin. So G begins with just a linear order term. And this linear order term must depend only on T, Z1, and Z2. So this is because, I mean, G has to be even. And so there can be no odd power of epsilon in G. So now we want to figure out what is this linear term. And this is basically the same as saying what is the quadratic term in the Taylor expansion of F. So the quadratic term will naturally be a Z0 to equivariant map from sim2 of the source of F to the target of F, right? The second symmetric product of the source to the target, because the second term of the Taylor expansion is naturally a symmetric bilinear map. And now if you just look, the right side is the sign representation, and the only component of the symmetric product which has a non-trivial Z0 to action is this one, which combines the non-trivial factor tensored with the sum of the two trivial factors. So here, trivial and non-trivial is with respect to whether they are the trivial representation of Z0 or the sign representation. So the quadratic term invariantly is described as a map from this tensor product to this co-kernel. And we can use a computation to identify this with the isomorphism star that we had before. So this isomorphism star could be alternatively viewed as a map from this source tensored with the kernel to the co-kernel. And this is something you can easily verify by a direct computation, is precisely the quadratic term here. And because now you can see the relevance of the choice of the coordinate W, which made this isomorphism star to be identity, that F is precisely given by epsilon times T Z1 Z2 plus higher order terms. So notice that T Z1 Z2 is a tuple that lives naturally in R to the 5, because Z1 and Z2 are both complex numbers and T is real. Okay, so we are not yet done. We need to have one more small detail before we can finish our analysis of the Konishi map, which is that we need one more Taylor coefficient before we can analyze the local structure of the zero set of F. So this is the following. So look at the first component of F. So that is the component which lies in this coordinate, so F1. And suppose I set T, Z1, and Z2 to be 0, then this is an odd function of epsilon, which vanishes to first order in epsilon, which means it starts from a cubic term because it's odd. And so it has a cubic term, a quintic term, and higher. And a simple genericity argument will show that actually this cubic term must not vanish. So it turns out what's relevant is only the sign of this cubic term. So I am going to just sort of safely assume that this is +1 or -1. And let us draw the picture for what the zero locus looks like in this case. So now the result is that W is equal to epsilon times T plus or minus epsilon squared, comma Z1, Z2. And so this tells me that W is 0 if and only if one of two things happens. Either the first factor vanishes identically, epsilon equal to 0. So this, remember, corresponds to just deforming the underlying embedded curve and just attaching onto it any branch cover you like, irrespective of what Z1 and Z2 are. Or the other possibility is T, Z1 and Z2 can be solved for uniquely in terms of epsilon. So what this means is that you get a picture that looks like this. So if lambda naught is +1, then this pink curve is actually representing the space of all double branched covers of the underlying embedded curve that deforms with the almost complex structure. And this blue is a sequence of curves which are lying in class 2A, which come and sort of crash into the curve sigma as the double cover sigma prime comma u at t = 0. And moreover, you can check that this curve will have sign +1. On the other hand, in the -1 scenario, when lambda naught is -1, you will see that there is no embedded curve of class 2A before t = 0, but after t = 0, a new embedded curve appears with sign -1. And so the nice thing is that the signed count of embedded curves of class 2A decreases by 1 when we cross the wall positively. So I want to just emphasize, therefore, that the sign of lambda naught did not really matter. What mattered only was that we crossed the wall, and that meant that the number of embedded curves changed by decreased by 1 precisely when you count with signs. Okay, so that completes our analysis of the wall crossing in this case, that is of the period doubling wall crossing. So right, so now we have so now I have a very brief section on an application of this. So so based on the discussion we had before, we can define what I think deserves the name, a virtual count of embedded curves of genus 0 and class 2A as follows. So step 1 is choose any super rigid J, and by Wendl's theorem, we know that plenty such exist. In fact, we can just choose a generic one. And then step 2 is define the number of embedded curves of class 2A in the almost complex structure J as follows. So this looks like a complicated formula, so I will define each term here carefully. So the first sum is just the signed count of embedded curves of class 2A. So this is a perfectly well-defined thing because we are in the super rigid regime. So J is super rigid. So we have a finite number of embedded curves of class 2A, and each of them has a sign associated to it. Okay, so that is sort of the naive count of embedded curves of class 2A. But now, as we saw, wall crossing can change this number. So we need to have a correction term which changes in exactly the same way as the first term changes, so that the two's difference will compensate one another. So the second term has contributions from every embedded curve of class A. So the contribution is as follows. So it is the sign of sigma. So this is plus or minus 1 times a quantity that I'll call W2 of the normal Cauchy-Riemann operator. So W2 stands for second wall crossing invariant. So what does this do? So you take the space of all linear Cauchy-Riemann operators on the normal bundle of this embedded curve, and then you choose a generic path from the normal operator, the normal deformation operator of the curve to a complex linear operator, which is rigid. So then you can take such a generic path and count how many times along this generic path does a 2-to-1 bifurcation occur. That is, how many times does this sign representation wall get crossed along this path in the space of operators. And this signed count is what is defined to be this W2. So what you can see easily is that this count is exactly rigged so that it compensates for the wall crossing difference in the number of embedded curves when we cross the wall that we just analyzed in the previous section. Okay, and so that was so I orally covered step 3, I guess, which is we need to check independence from J, and for this we use bifurcation analysis. So of course we need to also check that it's independent of the 2 other bifurcations that are listed, namely the birth depth for A and the birth depth for 2A. So birth depth for 2A, it's immediate that this is invariant, but for birth depth for the class A, we need to argue a little more. So yeah, and I'd also like to point out that in this case, we are actually able to identify this invariant that we defined very directly by counting curves and understanding their bifurcations. We can identify this invariant with the BPS invariant in this particular case. So in other words, we can actually write down a relationship between these wall crossing invariants W2 and the Euler classes of certain obstruction bundles. So that is what gives us the precise relationship between these counts and the Gromov-Witten invariants, or what is equivalently these counts and the Kobokumavalfa BPS invariants. Okay, so that is so that's a sample application that we can get from such bifurcation analysis. So further directions in which we are thinking right now. So currently in progress with Shaoyun, we are constructing Kurenshi models for general group representations. So this Z-mod 2 case was particularly simple, as you can see, because it was automatically Galois. So we did not have to pass to a further Galois cover and deal with the associated complications. Also, Z-mod 2 is a very simple group. So it's so we would like to deal with more general group representation. So this is something that is in progress. We would like to do this for all smooth domain curves and general genus. So we almost have a a complete description of such Kurenshi models, but yeah, I mean, there's still some more details we are ironing out. Another important problem is nodal degenerations or ghost components. So if you have a sequence of curves, so far we only considered when they limit to a branch cover of another embedded curve, but this branch cover itself has a smooth domain. What if this has, as Marco asked, a domain which is nodal? So then we actually need to, we no more can just do an implicit function theorem type argument. We need to actually understand gluing near such a nodal curve. So, and understand the obstruction map. So here we are trying to use obstruction bundle gluing to find out how precisely the moduli space looks like. So, so beyond this, we hope to use this to define integer valued invariants by counting curves with weights for Calabi-Yau threefolds in general. And also we would like to compare, as in my 2A case that I described above, with BPS or Gromov-Witten invariants. There are also some interesting integer valued invariants closely related to BPS, which are defined in Einel Parker's proof of Kobokumavalfa's conjecture. So another interesting question one might ask is, does this perspective on BPS invariants give us any idea to prove the finiteness of BPS invariants, which is another outstanding conjecture? So in this direction, there is some work by Doan and Walpuski from 2019, which deals with this finiteness in some special cases. So, and finally, one more thing that one can look at, and such techniques should be applicable for, are Kobokumavalfa type conjectures in higher dimensions, namely for Calabi-Yau 4-folds and Calabi-Yau 5-folds. So the references for these are from algebraic geometry. So Clem, Pandaripande, and the paper for Calabi-Yau 5-folds is by Pandaripande and Zinger. So yeah, so I think that's all I have to say for today. So maybe I will stop now. Thanks a lot.
Okay, let's thank the speaker. So thank you very much. So are there any questions for Mohan in the formal question session before we move on to the informal discussion?
So may I ask questions again in a somewhat similar point?
Mm-hmm.
Let us consider this holomorphic S2, which is a Galois cover of degree 5 over simple curve. The Galois group is a cyclic group of order 5. And cyclic group over 5 has 4 irreducible representation of a complex number. And each two of them is a kind of conjugate together. Yeah. A pair of representations over reals, which are not isomorphic. There is no real linear map between them. And my question is that why it doesn't happen that the linearized equation has a kernel of one of these two representations and the co-kernel is the other representations.
Let's see. So I mean, we can actually compute the index of a certain sort of twisted Cauchy-Riemann operator. So what we do is, so more generally, take any Galois cover sigma prime over sigma, let's say with group G, and take any representation W of G. So maybe let me write. So you have sigma prime over sigma and a representation G. Sorry, G is the Galois group, and it acts on W. So then you can form a bundle on sigma, or rather, I remove some points from sigma so that this, I assume this is just an unbranched cover outside of those points. And I descend W down to a bundle on sigma. So that is, I do something like this. So this is some vector bundle. And then I can look at my Cauchy-Riemann operator on this, right? Because this looks like just the Cauchy-Riemann operator twisted by a local system. And we can actually compute indices for these. So this will tell you that if a certain representation is occurring in the kernel, it necessarily will have to occur in the co-kernel as well.
So it means that if you consider this index as a K group of equivalent K group over G, then you can calculate this index as an element of equivalent K group.
Yeah.
So it's the kind of incomplete generality or some special situations are it.
I think it works in complete generality, but maybe I can't say a very precise statement right now, but I think it works in complete generality.
Okay, thank you.
So any other questions for Mohan?
I have a question. So what is the status of the bifurcation problem for more general groups?
Yeah. So
what needs to be worked out that hasn't been yet?
Right. So I think the main thing we need is, again, like earlier I had this genericity argument, which I did not elaborate in this talk, which is that a certain Taylor coefficient did not vanish. So that was sort of important to get the local structure of the moduli space, because just analyzing the quadratic term in that Kuranishi map was not enough, but one higher term was required. So so I think that in general is the issue, namely finding the next Taylor expansion term. For example, imagine a 3-to-1 cover of P1 to P1, which has Galois group S3. So so as in the Galois cover itself will be a genus 1 curve, but the non-Galois cover that we're looking at is just a map from P1 to P1, which is degree 3. Not the map Z goes to Z cube, but the one with generic ramification points. Then we are formulating a more generalized version of the Petri condition to make sure that the Taylor coefficient does not vanish. And I mean, we are right now in the process of going through the details of whether that goes through. I am fairly certain that it does, but I did not want to claim it here because we are still making sure.
I'd be a little bit surprised if it's just a matter of making the lowest possible order Taylor coefficient non-zero, because so what I've seen in the analogous problem for closed Rabe orbits, it comes down to a slightly more subtle singularity theory problem, where there's certain Taylor series that are stable and others that are not, but the generic ones are stable.
Okay.
But it's not so. It's not quite straightforward. It's not a matter of just taking the lowest order terms.
Okay. I mean, yeah, maybe you're right. I mean, maybe we need to think about this a little more carefully.
I suspect you basically need to be able to show that somehow that the k-jet of your obstruction section can be perturbed arbitrarily for arbitrarily large k. That would definitely be enough, I would expect.
Yeah, so I think that a generalized Petri condition type result, if we could prove, would give us that. But
I would also expect so.
Yeah. So that's exactly what we are actually looking at. So I mean, rather than looking at the problem of finding currency models, we are currently concentrating more on trying to iron out the details of that.
Okay.
Yeah. Mm-hmm.
Can you say maybe just a word or two about this these higher dimensional Kobokumavalfa conjecture? So I guess one thing I'm confused about is like in higher dimensions, it's you don't have nearly as many rigid homology classes, right?
Yeah. So there, I mean, you have something like so you take, I mean, let's so there you're looking only in very specific genera. So if you have genus 1 curves, so then the n-3 times 1 minus g, it's not the n-3 that vanishes anymore, but it's the 1 minus g which vanishes in the dimension formula. So now you're trying to look for integer structure within genus 1 Gromov-Witten invariants, and then and these will have some contributions from genus 0 Gromov-Witten invariants, which, as you point out, will not actually be rigid. So they will sort of sweep out a certain submanifold within my Calabi-Yau fourfold, which I then have to pair with either the second Chern class of the Calabi-Yau fourfold or some such characteristic class. And I mean, that's what will give me the numbers that I want on the right-hand side. So does that vaguely make sense? I mean, I don't, to be honest, I don't remember the precise formula off the top of my head, but roughly this is what it.
I see. So you're looking at specific genera that make the index 0, but then you get contributions from non-rigid classes.
Yes.
I see. Interesting. But and what about, if you're not in a Calabi-Yau manifold, is there any expectation that you should get these integer invariants? Or
so I mean, there are some things for so-called Fano classes. So yeah, but I mean, it's also the way they're usually formulated is you place enough point constraints so that it looks like it's a zero-dimensional problem, and then so for example, I mean, the Kobokumavalfa formula in genus 0 is this Aspinwall-Morrison formula. So I mean, one can formulate something very similar for Gromov-Witten invariants with point constraints also, Fano classes, as opposed to Calabi-Yau classes. So I mean, the precise factors there which relate the two generating series change a little bit in this, but it looks quite similar.
I see.
So in fact, I mean, this is explicitly commented upon in N.L. Parker's 2018 paper. So you can actually find precise statement there also.
I see. And they also prove something in that case, or?
Yeah. So they prove integrality for that as well. I mean, so what we are doing here is trying to actually count something that is sort of obviously an integer, rather than taking a number that is abstractly defined by an identity of generating functions and then trying to prove it's an integer. So our problem is sort of in reverse, which is we try to find something which is obviously an invariant and obviously an integer, and then try to compare it with, try to compare it using these generating functions. So.
Right. So you could also apply your approach to some non-Calabi-Yau space and try to recover the.
I think so. Yeah.
I see. Other questions? Okay, well, thanks again for the great talk.